Hello everyone, I welcome you all to the Unmanned Air Vehicle Design course. Today's lecture is on aerodynamic design of unmanned air vehicle. Fundamentals of aerodynamics. Aerodynamics is an applied science that studies the behavior of air in motion, especially when it interacts with solid bodies, like unmanned air vehicles. Unmanned air vehicles is an example taken here. If we take any arbitrary shaped body, and this is the airflow, right? So how this flow behaves when it interacts with the body surface. We'll have some wake region here at the behind of the object. One of the necessary tools in aerodynamic design process is the aerodynamic theories to calculate aerodynamic forces and moments. Aerodynamic forces are lift, drag, and moments are pitching moment. The aerodynamic forces on an object in an airflow, for example a wing, can be calculated from pressure distribution around the object. For example, let's assume this is the wing, right? This is the cross section of the wing. A 2D component, it is looking like an airfoil. So we'll have pressure, right? On the lower surface of the body, we have the pressure, and even on the upper surface, we have pressure, right? And at times it will be towards the surface, and at times it is away from the surface, right? So this pressure beneath this body, the pressure which we have, this will be higher when compared to this. Upper side will have low pressure, and at the bottom side will have higher pressure. And due to this pressure difference, the body attains some lift, but it lifts off due to the pressure difference. Understanding aerodynamics is essential to design efficient and stable unmanned air vehicles, and the design process requires accurate calculation of aerodynamic forces and moments. The aerodynamic forces of lift and drag of a lifting surface, for example, wing and tail, are functions of the following factors: surface angle of attack, which is denoted by alpha, then geometry, planform area, which is the wetted area. Suppose example, if this is the top view of the aircraft, and this is my wing, so this area, wetted area, is the planform area. Airfoil section, just now we have seen in the previous slide the airfoil section, the cut section of this wing, right? If we slice it here, we'll see the cut section to be like this. This is airfoil section. Airspeed, that is velocity of the aircraft, density of air, and Reynolds number of the flow. The lift and drag are determined by equations. L equals to half rho v square SCL, where rho is density, v is velocity, s is planform area, and c is coefficient of lift. And this drag is d equals to half rho v square SCD. Again, same parameters, v density, v surface area, and CD. CD is here coefficient of drag. This coefficient of drag is dependent on CL. We have equation, drag polar, CD equals to CD naught plus KCL square. CD equals to CD naught plus KCL square. This CD is dependent on your CL. CL and CD are lift and drag coefficients respectively. Drag coefficient is not constant it varies with lift coefficient, and the drag polar for a fixed wing unmanned air vehicle is given by CD equals to CD naught plus KCL square. This is zero lift drag. This is variable K, which is referred as induced drag correction factor, which is obtained from K equals to 1 by pi into E into AR, where E is Oswald span efficiency factor and AR is aspect ratio of the wing. Right? So this CD, from this equation you can see the CD is dependent on this K and CL, where K is dependent on Oswald's efficiency and aspect ratio. Right? Therefore, the CD is dependent on the aspect ratio of the wing and the coefficient of lift of the wing. The zero lift drag coefficient of a well-designed fixed wing unmanned air vehicle in clean configuration is 0.015 and 0.0025. Within this range, we'll have CD naught value. This CD naught value for clean configuration of unmanned air vehicle will have 0 in the range of 0.015 to 0.025. And for a quadcopter, the typical value of CD is about 0.2 to 0.4. This is CD value, not CD naught. This is CD, which is CD equals to CD naught plus KCL square. So here directly we are getting this value 0.2 to 0.4. The aerodynamic lift, drag and pitching moment on an airfoil is been shown in the schematic diagram. This is free stream velocity, V infinity is a free stream velocity which is passing through the aircraft wing, and this is the airfoil shape cut section of that wing, where L is lift force, D is drag force, and this is the resultant force. This is the resultant force due to pressure distribution. And this is aerodynamic center, and this M naught is, which is denoting the moment of the wing, moment of the airfoil in this case. The lift is always defined as a component of the aerodynamic force perpendicular to the relative wind. Right? So this is the lift which is perpendicular to this wind. V infinity is relative wind, and it is also called as free stream velocity. The drag is always defined as a component of the aerodynamic force parallel to the relative wing. This will be parallel to this wing. The aerodynamic center, which is frequently selected to be the center of lift, is located nearly at the quarter chord point. So from the leading edge, this is the leading edge. So from leading edge till here, this is C by 4. If we take this leading edge to trailing edge, if this length is C, chord, then this will be at the location of C by 4, the aerodynamic center. The wing 3-dimensional lift coefficient is directly a function of airfoil 2-dimensional lift CL. Right. We have CL, lowercase c suffix L represents 2-dimensional bodies. It is a 2-dimensional lift, like for an airfoil, and 3D lift coefficient is CL. CL is for the entire wing, entire aircraft. There is a difference between CL and CL. C suffix capital L represents the 3-dimension, which is for aircraft, and C suffix L represents for 2-dimensional. In turn, the variable CL is a function of variations of pressure coefficient on the upper and lower surface. Right, here there will be some pressure difference, and these pressure difference will generate the lift. Apart from that, this airfoil will be undergoing tangential stress and shear stress. For example, tangential stress will be like this, and there will be some shear stress on this which is denoted by tau. For the case of a small angle of attack less than 5 degrees, 2D lift coefficient is calculated from CL equals to 1 by C integral 0 to C CPL minus CPU into dx, where CPL and CPU are pressure coefficients at the lower and upper surfaces respectively, and C is airfoil chord. C is airfoil chord, this one, which is representing the chord length, the length of the airfoil from leading edge to trailing edge, or the shortest straight line joining the 2 points leading edge to trailing edge is defined as chord. The lift is produced due to the pressure difference between lower and upper surfaces of the wing and tail. It is same method we will be following for wing and tail. The variations of lift coefficient versus angle of attack is often linear, that is below the stall angle. This will be like this is CL, right? We are taking an example of an airfoil CL, and this is alpha, right? So let's consider a symmetric airfoil. It will be linear, and then there will be a curve and there will be dip in the lift curve. This point is called CL max, the maximum lift, and here it is alpha max, right? It is a point where we have the maximum CL, and this curve, it is dipping down, right? So this is stalling. Stalling is defined as there is a drop in the CL after attaining maximum lift. So this is stall angle. This will be almost nearby. There will be just a margin of fraction. Alpha max and alpha stall both are almost same. They are just separated by a fraction. This is alpha stall. Here, alpha stall is the angle where the CL starts dipping down. There is a decrease in the CL at that particular angle of attack. The UAVs are usually flying at an angle of attack below stall angle. So almost all aircrafts, all unmanned air vehicle aircrafts will be flying between this region, in this region, and we have a slope here. This is A0. It will fly between this region only, A to B. Unmanned air vehicle doesn't go to the CL max, or it will have any stall velocity or stall angle. The CFD softwares, based on the solutions of Navier-Stokes equations, vortex lattice method, and thin airfoil theory, are available in the market, which gives the accurate results on aerodynamic calculations. The application of such software packages are expensive and time consuming, but it will accelerate the wing tail design process. For example, we can use ANSYS, where we can create our body and our object, and we can analyze the aerodynamic analysis on that. We have also Abacus. This is Dassault Systems tool, which can be used for analysis, aerodynamic analysis, and also we can use open source tool, that is OpenFOAM. OpenFOAM is an open source tool which is available for CFD analysis. Wing design. During the wing design, aerodynamic design process, the following parameters must be determined. The first one, wing reference area, that is ES. What kind of shape my unmanned air vehicle will have, what kind of wing shape it will have? Well, it will be having a trapezoidal wing, it will have an elliptical wing, it will be having a rectangular wing. That I have to decide, and then I should freeze my design, like how the planform area looks like, for example. So this is the planform area, how it will be like, whether it will be a rectangular or it will be trapezoidal, like it will be trapezoidal, or it will be swept wings. Depending upon my design requirements, I'll be changing this planform area. Depending upon the design requirements, a designer will be opting for wing. Suppose it is for subsonic aircraft, so he may go with rectangular wings up to 0.5, Mach number 0.5, 0.4, 0.5. It is somewhere around 0.5 to 0.6 or 0.7. He may go with trapezoidal wings with little sweep angle, and again then the position of the wing will be coming into the picture, whether it is dihedral or anhedral, or it is a mid wing, straight wing, or it is having any aerodynamic twist, or it is having a geometric twist. It again depends on the requirement. The next point is the number of wings we need for generating the lift. Vertical position relative to the fuselage. For example, it can have high wing, mid wing, or low wing configuration. For example, if this is the front view of the aircraft, so if the wing is here, right, this is mid wing position. If it is here, high wing position. If it is here, it is low wing position. So low wing, mid wing, and high wing position. This is with respect to the fuselage. Horizontal position relative to fuselage. Cross section, what kind of airfoil what kind of airfoil combination the wing will be, whether it will be NACA 4 digits, NACA 5 digit, NACA 6 series, or any other configuration. Even that is dependent upon the design requirement. Aspect ratio, again we should know what aspect ratio is, because it directly affects the performance of the aircraft. As the aspect ratio is less, it will have good maneuvering capability, and if aspect ratio is increased, then there will be a compromise in the maneuverability of the aircraft. Taper ratio, tip chord. Tip chord is generally, if this is the fuselage, will have a different airfoil section at the fuselage where it is starting, and then at the tip will have different airfoil configuration. So here this is root and this is tip. Right. So this is in the fuselage. Right. We'll see in isometric view. This is the fuselage and this is the axis. Right. So here the wing is being inserted in the fuselage with, it is joined here using some rivet system. This is called root. This is tip, which is in free space. This is tip. The distance between this leading edge here to this trailing edge in the root is called root chord, and same applicable at the tip. The distance between this leading edge to this trailing edge at the tip is called tip chord. Tip chord. This is root chord. Yeah. Mean aerodynamic chord. Span. Span is the length of the wing. Suppose this is the rectangular wing which is for my configuration, right? So this is the span. This will be the chord. And then twist angle, which is alpha suffix t. Twist angle, alpha suffix t. Sweep angle. So based upon this reference line, this is the sweep angle on the either sides. Normally a rectangular wing will be looking like this. So this we have, instead of having it linear here, we have changed here like this. That's the sweep angle. Next, dihedral angle, again it is this is the aircraft front view facing the nose of the aircraft. For example, most of the commercial aircraft will be having low wing configuration, right? And this will be slightly up. This is dihedral angle. Similarly, most of the cargo aircrafts, logistics aircrafts, most of the cargo aircrafts, the aircrafts which carry the logistics, they'll be having high wing configuration, but they'll be slightly down. Right. So this angle here will have negative gamma. Here we'll have negative gamma. Okay, capital gamma it is, negative gamma, which will give anhedral angle. So it is represented by gamma. If it is positive, it is dihedral. If it is negative, it will be. So if it is positive, it will be dihedral. If it is negative, it will be anhedral. Incidence angle, IW, or setting angle, that is alpha set. High lifting devices, for example, flap, which is used to give the additional lift at the minimum speed, and ailerons. Ailerons we use for rolling the aircraft or banking the aircraft. The wing fundamental design requirements are lift, aerodynamic efficiency. Aerodynamic efficiency is L by D. Aircraft performance, stability, producibility, operational requirements, cost, and flight safety. These are the fundamental requirements of the wing design for any aircraft. Wing design is an iterative process, which means that the selections or the calculations are usually repeated several times. And as a designer, the aim should be to maximize the lift while minimizing the drag. This is the wing design procedure. First, we should identify and prioritize the wing design requirements. Then we should select the number of wings as per the requirements of the design. Then select the wing vertical location, whether it is low wing, mid wing, or high wing, depending upon the design requirements. Suppose in the case if it is a commercial aircraft which is a commuter aircraft, then most of the designs will be at low wing with dihedral configuration. And if it is a fighter aircraft which is capable of doing multi-role missions, then it will have mid-wing configurations. And if the unmanned air vehicle or the aircraft which is carrying logistics or cargo, then it will have high wing configuration with anhedral configuration. After that, select the design high lift device, whether you will be using flaps, ailerons, slats, slots, depending upon the lift requirement, we'll be adding and removing these high lifting devices. Then determine the sweep and dihedral angles. Once the configuration is freezed, lifting devices are added, then the sweep angle, dihedral angle is decided and tested. Once the testing is done, then select your wing airfoil section. How to select this wing airfoil section we will be seeing in the next lecture. Determine other wing parameters such as aspect ratio, taper ratio, wing incidence angle and setting angle. Then lift and drag and pitching moment are estimated. Lift is estimated, drag is estimated and pitching moment is estimated. And after that, based on all these parameters, once the requirements are satisfied, we'll go for optimization, or again we'll go back to select the number of wings. We'll increase the wing or we'll change the configuration, and then once it comes to optimization, then we'll calculate the span, mean aerodynamic chord, root chord and tip chord. Conclusion: a solid grasp of aerodynamic principles is the cornerstone of unmanned air vehicle design. By understanding how forces such as lift, drag and pitching moment are generated through pressure distribution, engineers can create unmanned air vehicles that are not only efficient but also stable and reliable in flight. Mastery of these concepts is essential for informed design decisions and successful aerial performance. These are the references used for this lecture. Thank you. We'll meet in the next lecture.